Alright, hello again, my cool cats and kittens, if you've seen the Tiger King. Welcome back to Unit 5. We are on Activity 30, which is all about transformations of quadratic functions. So, if you were in my class, this was one of the very last things we did. You'll remember this was the packet we did that had the donuts in the corner, and I'm going to call it the controversial donut packet because so many kids, this was a big grade for y'all, so y'all know what I'm talking about. So those of you that don't know what I'm talking about, don't worry about it because it's not that big of a deal, but my kids, you'll remember this was the donut packet that we did. So if you need to go look at that to help you with this, go for it. So basically these are transformations of quadratic functions, and we have what's called the parent function, f of x equals x squared. And when you graph that, it's going to make a parabola. The vertex is going to be on the origin. It's going to be opened up, and it's just going to look normal. Transformations is what do you do to the equation to make it go up, down, left or right, to make it go upside down, and to make it skinny or fat. So we have translations, we have reflections, and we have dilations or stretches. So so that's what we have. Those are all of our different transformations. Okay, so we have a little cheat sheet right up here. This equation is vertex form of a quadratic. And basically what vertex form is the easy way to show transformations. The A value is what stretches and shrinks it. So if it's greater than 1, it causes a vertical stretch. And if you think about a rubber band, let me go get one real quick. Okay, so if you have a rubber band and you stretch it vertically, it gets skinnier as you stretch it. So a vertical stretch makes it skinny horizontally. So it gets tall and skinny. A vertical compression or vertical shrink, if I were to push it together, it's kind of hard to see, it gets real fat. It's like a peanut butter and jelly sandwich. When you squish it, all the good stuff comes out the sides. So this gets short and fat. So yeah, so vertical compression, it's like a PB&J sandwich. As you squish it, all the good stuff comes out. There's a sandwich if you needed a visual. So yeah, so a lot of people get confused with the stretch and shrink, but we're talking about a vertical stretch. A lot of times people think that when it gets real wide, it's a stretch, but it's not. It's actually a compression or a shrink because we're talking about a vertical change. So it's getting shorter and fatter, or taller and skinnier. But we kind of notice the horizontal change more than the vertical change. Okay, so these values, your h and k, are your shifting values. If if h is positive, you shift left. Negative h shifts right. Vertical k shifts up. Positive k shifts up. Negative k shifts down. And then your a value, if a is negative, it's going to flip your entire graph. It's going to make it go upside down over the x-axis. Okay, so we are not going to graph it. Well, we could graph them if you wanted to. I could pull it up on Desmos. But it says for each quadratic function, describe the transformation of its graph from the graph of the parent function. So knowing that this is our original graph, so let me pull Desmos back up. We'll change this from last time. This is just x squared. So this is the graph of, well, you can't see that. So this is the graph of x squared. I wonder if I can change the brightness on here. That's not what I meant. That's much better. Okay, so this is the graph of x squared. So we're going to look, and what's this plus 7 going to do to x squared? Well, it's going to shift my graph up 7 units. Because this is my k value, it's at the end, and it's just plus 7, so we're going to shift 7 units up. And if you would like to see that graphed, we have x squared plus 7. So the blue, well, you can't tell the color difference, but we have our original graph, and then we have plus 7. It just shifted up 7 units. Okay, then we have this plus 4 in parentheses. So we have a positive h value, which means this is going to shift to the left 4 units. So shift 4 units left. Okay, so we're going to get rid of, let's go back to Desmos. So we're going to do parentheses x, not minus, x plus 4, close your parentheses and square it. And that shifted us 4 units to the left. Okay. Here we have x squared minus 4. So this is resembling this more than the other. So we should, instead of shifting up, we should shift down 4 units. Okay, and D, we have a minus 5, now negative h value, shifts it to the right. So this shifts 5 units right. Okay, and you can check that in Desmos. I'm just not going to, because we're this is going to be a lengthy episode anyway. So, all right. So let's move on to part 2. Let's turn my light back on a little bit. Okay, so we want to complete the table, then graph each function on the same coordinate grid, and then complete the second table. Okay, so this one's going to be easy. We're just squaring x. So negative 3 squared is 9. Negative 2 squared is 4. Negative 1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. Okay, then we have x squared plus 3. So we're going to square this term and then add 3 to it. Now the good thing is we've already squared the terms. So negative 3 squared is 9, and 9 plus 3 is 12. Negative 2 squared is 4, plus 3 is 7. Okay, and we keep going. We'll just add 3. Just add 3. We'll just add 3. So we're going to graph. I'm going to graph f of x in purple. We'll graph g of x in blue. And so we're just going to plot these points. So we have a point at negative 3, 9. Negative 2, 4. 1, 1, 0, 0, 1, 1, 2, 4. And then I will tell you, it is all quadratics are symmetrical, so you should have a point at 3, 9 as well. That's 3, 10. This is 3, 9. And we're going to connect. All right, so there's f of x. Okay. All right, so g of x, we're going to do the same thing. So at negative 3, we have a point, 1, 2, 3, at 12. At -2, we have a point at 7. At -1, we have a point at 3. No, I'm sorry, at a point at 4. And at 0, we have a point at 3. And then it comes back up. Okay. Alright, so let's look at our first equation. We want the vertex of f of x. So that vertex is that bottom point. That's our minimum. So our vertex is at 0, 0. Okay. Our domain. So if I were to zoom this graph out, and actually I can do that. Let's close this one out. I can do that on Desmos real quick. If you were to keep zooming out, this graph is not going to end. So it looks like it's getting skinnier, but remember, I'm zooming out. I guess a better way to say is if I were to keep traveling, this is going to eventually touch every point on the left and right. It's really kind of hard to see. Let's go back home. This is going to keep getting wider and wider and wider as I scroll up. It's going to keep getting wider. If I were to zoom in, I'm still going to get wider and wider and wider. So it's eventually going to touch every single x value from -infinity to positive infinity. So my domain, I'm going to use this symbol, which most of you have probably never seen before, but this stands for all real numbers. Okay, and I would normally do in bracket notation, but there's just not a lot of room here. Okay, so my range is not going to be all real numbers. If you look, again, using Desmos, I can keep scrolling up, and these aren't going to end. I should always have a point as I go up. However, there is nothing below 0. Once 0 is my lowest point on this graph. If I go down, I don't have any function. So my lowest point is 0. So I'm everything above 0, which means y is greater than or equal to 0. Okay, and then I have axis of symmetry, which I don't think we have talked much about in the videos. You probably did get to some of this before you left, I say before you left, like it was voluntary, before we were told not to come back up to school. But the axis of symmetry is an imaginary line that runs through the vertex. It goes through the center. And basically what happens on the axis of symmetry is that if you have a point to the left, there is a point equally as far away on the right. So here I have 2 points. I have a point that's 2 units away from the left. I should also have a point 2 units away from the right. And so it should be symmetrical of that imaginary line. So that imaginary line runs through the axis of symmetry, and it's an imaginary vertical line. So it goes to the vertex, and it's a vertical line, so we're going to have x equals, because when you have x equals a number, it draws an up and down line through that number. So the x coordinate of my vertex is 0, so my axis of symmetry is x equals 0. Alright, so let's look at those same features for my g of x graph. My vertex is not 0, 0. It's been shifted up, so my vertex is 0, 3. My domain should not change. It should still, as I zoom out, it should still get further and further. It should still go from -infinity to positive infinity. So again, I can use all real numbers here. Okay, my range, it's going to be kind of similar. It's still going to increase forever. It's going to reach infinity. But when I come down, it's going to stop at 3. So 3 is the lowest coordinate. So my range is going to be y is greater than or equal to 3. And my axis of symmetry, again, it's just like on this one, it goes through the x coordinate of your vertex, which here is 0. So my axis of symmetry, I don't know how I said that last time, is x equals 3. Alright, so let's move on to the next page. So as we shift up and down, the only thing that really changes is our range and our... Okay. I knew it. It should be x equals 0 because that's the x coordinate of our axis of symmetry should be x equals 0. That's the x coordinate of our vertex. And I knew it as soon as I was catching myself. So the only thing that should change is the vertex and the range. The axis of symmetry and domain should be the same when you shift vertically. Sorry about that. I knew it in my head and just wrote and said the wrong thing. Oh, goodness. COVID-19 brain. I'm like, well, quarantine brain. Let's call it quarantine brain because I don't have COVID-19. I don't think. My brain is mush. Okay, number 3. Alright, complete the okay, so this is just like the last problem. Were we supposed to compare? It didn't say to. Okay. So this is just like the last problem. We're going to plug in some points and graph it. And actually, I'm going to cheat a little bit because on this column should be almost identical to, well, it should be identical to the column from the last problem because this didn't change. Okay, so now we have negative x squared for g of x. And so all that means is I take my number, square it, and then make it negative. So these should be the same points, just negative. Don't make 0 negative. There's no such thing. 0 is just 0. But everything else we're going to make negative. Okay. So, again, these things from the previous page don't change because this is the same function. The only thing that should change would be this column and on the graph. So when we graph it, so we have a point at 0, 0 again. We also have a point at -1, -1, and at 1, -1. And that's all we can fit on this coordinate grid. However, if you wanted to, we could, let's do this. Let's do it on Desmos. And there we go. And so this is what it would look like. Alright, so let's talk about the vertex. The vertex of negative x squared is still 0, 0. That didn't change. The domain should not have changed either. And let's look at the range. This one doesn't have a minimum. This is upside down, so it has a maximum. And it does not go to positive infinity. In fact, I'm going to hide the original function. Once you hit 0, you don't go any further up. That's the highest. So instead of y being greater than or equal to 0, our range is going to be y is less than or equal to 0. Because 0 is the highest point, and then this goes on forever downwards. And then my axis of symmetry still hasn't changed. It's still x equals 0. Okay, so it says compare the functions above. We could say it's mirrored or reflected. The y values are now negative. Okay, and the range has changed. In fact, the two functions only share one range value, and that is 0, 0. That's 0. Alright, number 4, same concept. We're gonna graph functions. Okay, so this one should be a little bit different. We still have 0, 0. Negative 3 squared is 9, positive 3 squared is 9, 6 squared and negative 6 squared are both 36. So let's look at this. This was a very, I don't understand why we got those values. I feel like that should be 1/3, but I could be crazy. I wonder if the x values for this and the next one mixed up. That's okay. Alright, so this is 3x squared, which means we take all these points and multiply them by 3. So 0 times 3 is still 3. 9 times 3 is 27. And 36 times 3, 108? 108. Okay. Which is going to be a pain in the butt to graph on here, but we're going to do it. Okay, let's see. Yeah, I'm looking. I think these tables from here and here got mixed up, because this would be a lot easier numbers to do this. So, let's go ahead and do 1 and 2. Okay, so 1 squared is 1, times 3 is 3, 2 squared is 4, times 3 is 12. I said 3 and wrote 3 instead of 2. Okay. Alright, so when x should still have a point at 0, 0, because 0 times 3 is 0. Okay, 1 squared is 1, times 3 is 3. 2 squared is 2, or is 4. Times 3 is 12. Okay. So I did some extra work in there. It made this look a lot nicer and neater, though. It made it a little bit easier to graph. Alright, so what do we notice real quick? If we're looking at this, we could say g of x is skinnier than f of x. And let's just go ahead and graph on Desmos just so we know I'm not being biased. We're going to turn this to 3x squared, and boom, it is a skinnier graph, which is what we wanted. Okay, so our vertex is, so this should all be the same because this is f of x. So vertex is 0, 0. Domain is all real numbers. Y greater than or equal to 0. Axis of symmetry is still x equals 0. In this column, our vertex is still 0, 0. That hasn't changed. Our domain hasn't changed. Even though it's skinnier, remember, it's still going to get wider and wider and wider. It's just going to take it a little bit longer. It's going to hit your y value before, it's going to get taller before it gets wider. So it's just going to take a little bit longer. But it still should be all real numbers. My range has not changed because 0 is still the lowest y value. And my axis of symmetry has not changed because we haven't shifted left or right. So those should all be the same. Alright, so what I'm hoping you notice is that if I give you the vertex, axis of symmetry, domain, and range, you still don't really know much about the function because these all have the same values here, but they're two totally different functions. So you do need a lot more than just these features to know about your function. Alright, number 5. Okay, so we know these values. We know these. Go ahead and fill this in. Okay, so this is 1/3 of x squared, which Again, probably should have used the graph from earlier, or the table from earlier. Which means we're going to take these values and divide them by 3. So 0 divided by 3 is still 0. 1 divided by 3 is 1/3. And 4 divided by 3 is 4/3. So something else I want to do, let's go ahead and get values for -3 and 3, just because I think that will help us out in the long run. That'll be the easiest thing to graph. So -3 squared and 3 squared are 9. And 1/3 of that is +3. So we have a coordinate at -3, 3 as well. I just want to use that too. So we have coordinates at 0, 0. We also have coordinates. We'll go all the way out to -3. 1, 2, 3, and up. 1, 2, 3. 1, 2, 3. 1, 2, 3. That's going to be the easiest thing to graph. Okay, so comparing these, this is a wider function. Well, we'll say g of x, sorry, or h of x, sorry. H of x is wider than f of x. Okay, so let's go back to Desmos. So we're going to do 1 divided by 3. X squared, and it does make a wider function. Alright, so let's come over here. Vertex stays the same. Domain. Every quadratic function, until you get into real world problems and it asks for a reasonable domain and range, where you have to cut the domain somewhere for the problem to make sense. If that's not happening, if it's not a word problem, if it's just a graph, or just the function, the domain should always be all real numbers. Now the range should change some depending on the function. This one it's not going to, because again the lowest value is 0. And again, we didn't shift left or right, so my axis of symmetry stays the same. Okay. Alright, should be getting close to the end now. Alright, so this asks us to identify the transformations from the graph of the parent function to our new graphs. So what has changed from here to here? So let's look. What we have now is this +1 in parentheses. So remember, when we add 1 on the inside of parentheses, it shifts, or when we add or subtract on the inside, it shifts left and right. So this is our horizontal translation. So it's going to shift. So normally we would think that it would shift right because it's positive, but remember, horizontal goes backwards, so this shifts left 1 unit. So shift 1 unit left. And then we have this +4 at the end. That's our vertical translation. So that means it's going to shift 4 units up. So my vertex is going to be at -1, 4, because it goes 1 to the left and 4 up. This is why this is called vertex form. This actually gives you the coordinates of the vertex, and it's pretty awesome. Alright, so then we have our next one. We have y equals -1/2 times x minus 1 squared plus 1. So let's look. First thing I notice, we have a negative symbol, which means this is reflected over the x-axis. So this should be, it should be an upside down parabola. Then we're multiplying by 1/2. So we're multiplying by a number that is smaller than 1 but larger than 0. So since this is smaller than 1, and we're talking about the absolute value, let's ignore the negative, but 1/2 is between 0 and 1. So that means this is a vertical compression. It's a vertical shrink, so it squishes. So it should be a fatter graph. So this is a vertical compression of 1/2. Okay, and then we shift. This is a -1, so instead of shifting left, we shift right. So we shift right 1 unit and up 1 unit. That +1 shifts us up 1 unit. Okay, and if you have time, I would plug these into Desmos and just double check that and just kind of look at what those look like. All right, number 7, for the quadratic shown in the graph, write the equation in standard form. Ooh, so this is going to be fun. So they did give us the vertex, and they did give us a random point. So we're going to use vertex form. So y equals a times x minus h squared plus k. Okay, so let's just look at this for just a minute. So we don't know what the a is going to be, but we do know our vertex. So our vertex is -1, 1. So let's plug our vertex in. So my h value is -1. And my k value is +1. And so we have a times x, negative is positive, so x plus 1 squared plus 1. Okay, which sounds great, but we need to fill that a in. We don't know if there's a stretch or not. There appears to be. So let's fill in our point and see if we can solve for a. So we have a x and y coordinate of 3. It's still an a. And our x is 0. So let's start solving. So we have 3 equals a times 0 plus 1 squared plus 1. So let's do 0 plus 1. So we have 3 equals a times 0 plus 1 is 1. We have 1 squared plus 1. So 1 squared is 1. We have 3 equals 1 times a, which is just a, plus 1. We subtract 1 from each side, we get a equals 2. So my vertex form of my equation is y equals 2 times x plus 1 squared plus 1. So we took what we got here and we just filled in that a value. So I'd like to say that we're done, but it asked us to write the equation in standard form, and this is in vertex form. So I've got to get this into standard form. Remember, standard form is ax squared plus bx plus c. So I've got to try to simplify this into this. So the first thing I would do, let's just follow order of operations. Let's use that exponent. Now, I know a lot of people are going to be tempted to do x squared plus 1 squared, but that's not what this says. This says x plus 1 squared, which means x plus 1 times x plus 1. So we're going to do 2 times whatever x plus 1 times x plus 1 is. And then we'll make sure we add 1 at the end. Okay, so you could do a few things here. You could FOIL it, you could distribute, you could do box method. I'm a personal fan of box method, so let's do x plus 1 times x plus 1. X times x is x squared. X times 1 is x. 1 times x is x. 1 times 1 is 1. Okay, and then if I combine my like terms, I have x squared plus 2x plus 1. So let's take this. We have y equals 2. Let's replace this piece with what we just found out. times, so we have 2 times x squared plus 2x plus 1. And then we have this plus 1 at the end that we do not want to forget. All right. I would distribute my 2 next. So we have y equals 2x squared plus 4x plus 2. And then we have that plus 1 at the end. Combine that 2 and that 1 in our equation in standard form for the final answer. Is that. Okay. Alright, so I'm going to leave you here. Good luck with the independent practice. If you have any questions, feel free to email your math teacher or email me. Stay safe, stay healthy, and thank you for your attention. I hope you guys have a good day.